Questions? We're running out of days. The exam's Monday. Over chapter 2. All right. So the one thing that we ended on last class was the idea of proof. Real numbers are uncountable. And it ends up that, okay, this is enough to prove the reals from 0 to 1 are uncountable. What are the reals from 0 to 1? The reals from 0 to 1 are r are equal to 0 point, say, decimal 1, decimal 2, decimal 3, etc. So every r looks like that, except we exclude all infinite 9 versions of terminating decimals. Sorry, terminating, decimals. For example, 0.12 is actually equal to 0.119 repeating. So what we do is we say none like this. By doing that, so it's enough to prove that the reals from 0 to 1 are uncountable. Everybody looks like a 0 point something, except we're going to exclude all the infinite 9 versions of terminating decimals. 0.12 is the same thing as 0.119 forever. So let's just throw out that one. By doing this, now all these decimals are unique. So we need that part to be able to begin to prove, right? We need to simply say, what are we dealing with? We're dealing with things that look like this. And so we do a proof by contradiction. Again, what's a proof by contradiction? In a proof by contradiction, your goal is that not the case reals are uncountable is logically false. That's what you want to get to. But really what that means is, what is your actual goal? Your actual goal is reals are countable is logically false. That's your real goal, right? That's the idea of contradiction. Why is this called contradiction? Because what does it mean to be always false? Contradiction. That's what the word contradiction means. It means in all cases we have a false. So that's what I want to do. All right, so we'll start off with the assumption. What can we assume? We can assume the hypothesis, and we're going to say, okay, I'm going to assume that R is countable. If we assume that R is countable, what does that really mean? That's logically the same thing as there is a bijection from the counting numbers 1 to 2, these R's between 0 and 1, right? And when I mean R, we're always talking about R restriction, right? Between 0 and 1. That's where we're looking right now. All right, if that's a bijection, that really just simply means you have a list. You have that, if we would write it in list form, right, you would say that, oh, look, there's a roster version for the R's. There's R1, there's R2, there's R3, there's R4, ... right? I have a roster. It's real 1, real 2, real 3, real 4, and not only this, all are all reals between 0 and 1 are here, right? That's what it means to be countable. First, second, third, they're all here. From here to infinity. We've counted them all. All right, what's the problem with this? Well, we sit back and say, all right, let's look at them this way. Real 1 obviously is 0.11, decimal 12, decimal 13. Real 2 is 0.21, decimal 22, decimal 23. And then this would continue on forever. All right, given that we have this, we're going to lead to our contradiction. Consider R star. And the book, in their example 5 from 2.5, does this proof. And they go through this like what I talked about last time. I'm going to make an R star that is definitely not R1, and is not R2, and is not R3, and it's not going to be anything. And so I'm going to create this. And the way that I do this is consider this guy here, which is 0.D1, D2, D3, etc. Except I'm going to do the following thing. Like I mentioned last time in class, I'm going to pick D1 so it is not D11 and not 0 and not 9. Why am I staying away from the 0s and 9s? I really could just stay away from the 9s, but why am I staying away from those? Right, there's the issues of the terminating decimals, right? I could sit there and accidentally get an infinite number of 9s, and it's one of the terminatings that I already counted, but it's actually there, and I said it wasn't. So I'm going to stay away from that issue. All right, now comes the question of how do I pick D1 so that it's not D11? Now, if I did that, if this was true, hey, look, D1 is not D11, by uniqueness, real 1 cannot be R star. Does that make sense? If you differ in one place, you can't be that number because we have uniqueness from way back here at the beginning, right? We have uniqueness of decimals. So if you change in one spot, it cannot be the same. Now, here's the question. I can say this, pick a D11 that's not D11, but the book would say, or some mathematicians would sit down and say, give me an algorithm. Tell me how you're going to do that. You tell me you're not, well, I don't like that. You have a lot of freedom, pick something that's not there. Well, tell me how you would do it. Give me a process. And so what they do is for the book, I think they pick what? Let me look. They use two numbers to do that. What do they use? Example 5, that's the continuum hypothesis. Yeah, they use the numbers 4 and 5. And so what the book does, what do you mean by this? How to do this? Personally, I'm okay with this saying, pick D1 so it's not D11 and not 0 and not 9. The way the book does this, the book version is to make a piecewise defined function. D1 is 4 if D11 is not 4. Make sure I get their notation right. Yep. On the other hand, what happens if D11 is 4? Well, let's pick a number that's not 4, and then go ahead and pick 5. Can you see how that process is? You look at D11. Is it not 4? It's not 4. Okay, you pick 4. Is obviously D1 and D11 different? One is not a 4, one is a 4. They're different from each other. Then you look at D11 and say, well, no, I see a 4. Okay, then write 5. Are 4 and 5 the same? No. Now, does it need to be this? This would be a function that, do you notice that this function satisfies this, this, and this? Is D1 ever a 0 or a 9? No, it's going to spit out a 4 or a 5. Is it always different from D11? Yeah. If D11 is a 4, I pick a 5. If it's not a 4, I pick a 4. Those are different from each other. Did we need to do 4 and 5? Is there anything special about those two numbers? No. So if you wanted to, really any version could be just simply, all right, if D1, I'm going to pick, all right, pick two numbers that are not 0 or 9. 3. And what's your other favorite number? 7. Okay, if D11's not 3, pick 3. On the other hand, if D11 is 3, pick 7. Where do I get? I'm sorry, no. That's a tautology. We always need more coffee. Actually, no, caffeine's toxic, so you get too much coffee, it actually. Caffeine will kill you. So. Too much water. That's a terrible way to go. So, every now and then, marathon runners kill themselves by accident, by water loading. It's like, if I drink a lot of water now, I won't have to stop while I'm racing. And they drink too much, and then they die. All right. So we need to have a campaign to ban dihydrogen monoxide. Sorry. Really, anything you want. You just sit there. Is everybody okay that if you look at the book, why in their proof did they pick this? Because really, what is their goal? It needs to satisfy those three things up above. Anything that you could possibly think of that does those three things in an algorithm would be an algorithm that would work. And I really don't, now for myself, as long as you understand that it's those three things, I am personally okay if you guys would simply write, I am going to pick D1 so it's not D11 and not 0 and not 9. How do you do that? I don't care. Just do that. Like if you see a 5, I'm going to pick something not 5. But if I see a 7, how about you pick something not 7? Right? You just stay away from the number that you see and then 0 and 9. You have lots of choices, right? You have 7 other numbers that you could pick. So that's fine. Now, on the other hand, by doing it this way, you could say that, so for any DI, we would just simply do this. If we stick to the book algorithm, let's stay with the any version. Let's pick the 3 and 7. If DII is not 3, I would pick 3. If DII is 3, I'll go ahead and pick 7. And then we can actually see that. So we see that for any I, DI is never DII. But that implies by uniqueness of the decimals, this real star is not any of the reals in your list. Is everybody okay with that? So really all you would have to say is up here, is you would say, like on this one, pick DI so that it is not DII. And not 0 and not 9. If you do that, for all I, you could immediately go to this point right there. We see that for all I, DI is not DII, because that's what I'm doing, picking something different, and not 0, not 9, and by a uniqueness, that's not that. But, which is actually the word and, but it makes a point here, please focus on the next thing. R star is between 0 and 1. So what's my problem? This. these RIs are what? All of the reals between 0 and 1. Well, hey, look. What's R star? Between 0 and 1. And what else do I know to be true? It's not in the list. Is that possible? I have all of them. And here's this number between 0 and 1 that's not there. You know, that's logically, that's why I put the word but, because to make a point, this leads to the contradiction. Therefore, false. So what have you said? If it's countable, it means this, which means this, which means this, which means this, which means, oh wait, false. So we're done. So reals between 0 and 1 are uncountable, which would then imply the reals themselves are uncountable, which is what I wanted to show. Because if a smaller thing is uncountable, the bigger thing is uncountable. So this is just a little bit more of an explanation of example 5 out of the textbook. Why am I doing this strongly? Because on the first exam, either one or both, prove the rationals are countable, prove the reals are uncountable, are going to be on Monday's exam. All right, so for accountability, we have the idea of what things are uncountable, what things are. Also at the end of this, for anybody who's going on to Discrete 2, it's going to review some of the homework problems on this, and it talks about in this section the idea of computability and uncomputability of functions, whether you can write a program. You're going to review this for this, and the idea is really, what's kind of the idea of computability, which is you can write a program. Computable function says, okay, I have a function of n that spits out, I don't know, say b. So I have this function here. So that's a function, and the question is, can you write a program to do this? And what happens is the following. If I would consider the real numbers are actually made up of a disjoint union of the rationals union the irrationals. All right, the reals are what? Uncountable. The rationals, on the other hand, are countable. If I have a set that's countable in its cardinality, and I have another set that I don't know its cardinality, but I know that when I put them together they become uncountable, what do I know before? Well, if I took a countable and a countable, which we've done before, right? If I give you two countable sets, you would just stack them on top of each other and count them. 1, 2, 3, 4, 5, 6, right? So two countable sets must be countable. So what would that tell you about the irrationals? They're uncountable. So that would immediately tell us that these are uncountable. All right, this leads us to, you kind of look at this and you ask, well, so what? Well, you can consider that any real, which is, say, 0.d1, d2, d3, right? We knew that these things were, these we know are uncountable. But if I looked at this, I could consider this acts like a function. What it is the function based upon this real does the following thing. It just simply spits out dn of n. So I could consider this a function. I could say, what is f of 1? Go to the first decimal, tell me what number that is. Okay, what's a D of 10? 1, 2, 3, 4, 5. In the 10th position, what decimal is that? So this real number actually stores a function. It just simply says what decimal is in what position. This particular function, f of r, is mapping the z plus 2, 0, 1, up to 9. That's what it does. That's all this thing does. It's from this set to this set. But if these reals are uncountable, how many of these functions are there? Uncountable. So that tells us that there are uncountable functions like this. That's an incredibly simple function. It just simply takes an integer, a positive int, and spits out a number between 0 and 9. How many of those functions are there? There's an uncountably infinite of them. The problem with programming is this. If you're your concept of programming is to have an infinite number of monkeys pounding on an infinite number of keyboards, right? Well, you look at the keyboard. How many keys could they possibly hit per stroke? 1. Even though you would look at your program and you see things like hard return and tabs, those are actually what? Single strokes. So every program is actually a what? A sequence of keys that a thing is hit. So how many first keys do you have? Is it finite? Yeah. How many second keys do you have? Finite. It doesn't matter if I look at this. A program is made up of what? If I went for infinity, we could, but in the end, it's a finite set of finite things. And even if I did that forever, it must be at least what? Countable. So even randomly beating on the keys, whether the program will compile or not, doesn't mean anything. It simply says, for every program that could ever possibly exist, it has to be countable. So there's my problem. But programs do you see the problem? How many functions can you code? A countable number of them. But how many functions of something as simple as this exist? Uncountably infinite. So what could you do? Countably infinite programs, but I have uncountably infinite things that I'm interested in. So what does that tell you about functions? If we go back to here. If what you want to do is uncountably infinite, but what you're capable of programming is only countably infinite, what does that tell you about things that you're interested in but you are incapable of doing? They're uncountably infinite. And those are just simple functions, let alone what about the entire world of things that you might be interested in? In other words, that just simply tells you what computing programming has a very large part of, especially within mathematics, is could you even do it? There's only a countable concept of them. There is an uncountably infinite that aren't approachable by technology. There's nothing you can do. You just can't do it. Why? It's a counting problem. It's just not capable of doing it. And so a lot of mathematics will be, if it's impossible for you to do computationally, can you do something close to it that you can do computationally that gives you a reasonable approximation of the reality? That, in other words, you know it's wrong, but how bad is it? Which is, error approximation. And we start to do problems of this nature. Examples of this would be, say, weather. We know that in about 5 days, it doesn't matter if we had a perfect computational model for weather, all of your measurements that go into it are wrong, right? You go out and you take a temperature. Is that actually the temperature? Go stand next to the building in the sun. Go stand in the shadow somewhere else. Go stand in the wind and underneath the trees somewhere else, all within 100 feet of each other. What's the temperature? Okay, so you plug that into your algorithm. That's not the temperature. What happens within every time this feeds into it? What's tomorrow? Well, that's wrong. Well, I had to feed tomorrow to get the second day. But your wrongness grew. That's right. And we can mathematically show that within 5 days, your algorithm is just as accurate as a person saying, I think it will be 75 degrees, because he guessed, right? And if you're as accurate as a person just simply guessing, you aren't predicting anything. So, actually, if you look at long-term weather predictions, why do they go out past 5 days? We know mathematically that 5 days is about the algorithm. If you notice, if you look out 5 plus to 10 and then 12 days, you'll notice if you would go and look at the Farmer's Almanac that said, this time of year it's about going to be this temperature, you'll notice that it always tends to that. Why? Because that's the smart thing to do. Guess reasonably. And so your 2-week outlook is a reasonable guess. And usually it's more accurate than the computational model, which is funny. All right. So that'll be one of the things that you actually have to go through this argument and actually prove it. All right, some other tools that we need to know is 2.6. It's just a review of matrices. This is not a class in linear algebra. All right, we're not doing linear algebra. We're only going to do as much as necessary. Don't throw the very expensive pen. That's the bad thing about having Wacom pens. Like, oh, it's broke. Yay. All right, it's not broke. All right. So we're only going to do enough linear algebra to do what we're interested in. So all we're going to talk about, we're not going to get into the hows and the whys and everything else. Linear algebra is a really good course where I sit there and say things like math is toys and rules. Linear algebra is nothing but the toys and rules in all the different ways. You rethink what an algebra is, and you say, oh, this is a vector space. Well, what's a vector space? Anything that satisfies this concept of toys and these concepts of rules, and it's not really a vector. It could be a polynomial or a continuous function or things like that, right? So that's why you usually when you say vector space, you put little scare quotes. Vector-like, right? It's not actually a vector. It's a polynomial. That's not a vector. But it satisfies the things that we're talking about. Now for us, we're only going to talk about the basics, and we're going to talk about our objects. For us, again, this is not linear algebra. We're going to narrow it down to one specific type of and concept of objects, which is a matrix, which is a rectangular block of numbers, or we're also going to not use numbers. We're going to use bits. So either the rectangular block is going to have numbers inside of it, or we're going to possibly do bits, which is 0 and 1. So those are the two types of matrices we're going to talk about. If it's a numbers, this is just simply a matrix. If it's a bit, we're going to call this a 0, 1 matrix, because it's a bit 0, bit 1 matrix. And if I write a matrix of zeros and ones, it could be the number 0 and the number 1, or it could be the bit 0 and the bit 1. So usually I'm kind of lazy. I'll give you a matrix of zeros and ones and say, well, this is a matrix. Please do addition and multiplication. And then I go, oh, wait, it's a 0, 1 matrix. Do meets and joins and Boolean products. And so we'll talk about the ops on that. All right, so now that we know what our objects are, what do they look like? Well, how do we write matrices? Matrices are made up of lots of little elements, which are A11, A12, up to A1n, down to AM1 over to AMN, right? And this is M by N. M is the what? Rows. N is the columns. And this is always row, column, row, column, row, column. And so we say row, column, element-wise positions. So if I say A35, third row, fifth column. All right, so that's when we spit out where it's at. So that's what a matrix looks like. Whether the aij's are numbers or bits, it's a matrix. And we call it a matrix or a 0, 1 matrix, depending on what's on the inside. All right, so that's what we got. Now comes the question of, all we're interested in this class is we are going to, the whole point of this is we are going to take things that interest us and represent them by matrices. We're going to take graphs and represent them by matrices. We're going to take a lot of different things and represent them by matrices. So we have to have and so all we're going to do is, given this, we're going to do particular operations. So if it's a standard matrix, the operations that we're going to talk about are A plus B. Okay, what has to happen for an A plus B? For this equality to happen, what's the first thing that has to be true? Yep. Rows and columns have to match, so it has to be same size. And then what do you do? Take exact positions, layer on top of each other, add. That's all we're interested in. Can you do this? So this is what I want you to be able to do. Take a matrix and another matrix and add them. That's all. All right, the second one would be multiplication. Multiplication is not same size. If this is m by k, this must be k by n. What has to happen? To be able to appropriately multiply, k on A represents the who? Columns. K on B represents the rows. The number of columns of A must match the number of rows of B. This will then create a matrix, call it C. But what is Cij? Cij is the inner product of A's ith row and B's jth column. What is the inner product? The inner product is you go in the same order, Cij, and what is A's ith row? A's ith row is I row 1, AI 2, AI 3 up to AI k. Everybody okay with that being A's ith row? What is B's jth column? B first row and j column, B second row j column, B third row j column. I'm going down the column, but how many are down there? There's k of those. And then what I do is I take the inner product. Multiply same positions where we're talking about first element, second element, third element, right? The first element of A's row, first element of B's column. Then the second times the second, and the third times the third. When we look at it, it looks something like this. If this is A, and this is B, whoop, that doesn't look like a B, does it? B, we go across this, where we have 1, 2, up to K, and we take this one, and then we have 1, 2, down to K, and this is the I, this is the I, and that's the J. What do? I just go, use your fingers, go that times that, plus that times that, plus that times that, plus that times that. And then we get that one ij element. Is it computationally expensive? Yes. Why is this the complicated version? It'd be nice if it was same size and you just multiply like you did add. That's called a dot-wise product, right? That does exist, but that's not what we're interested in. Why? Take linear algebra. If you're interested in why this definition is, there's a nice long definition about this is solving systems of linear equations. This is a natural definition of a multiplication because of that. And so it needs to make sense, and it makes sense for that application. And it ends up being very useful. All right, so that occurs for matrices. What if it's a bit matrix or a 0-1 matrix? This idea of a 0-1, again, these are bits, bit 0 or 1. All right, for a bit 0 or bit 1, does plus make sense? There is no plus for bits. What are the operation for bits? Bit and, bit or. Those are the operation for bits. So if I look down here, what about product? times plus makes no sense. I have bit and bit or. I do not have a times and a plus. So what should we do? Well, what we'll do is say, the first guy, we're going to simply say, how about matrix A and matrix B, and I won't say what that operation is, but what I'm going to do is I'm going to take my Aij and do a bitwise and between Bij. In other words, we need same size. And that, in terms of the 0, 1 matrix, instead of calling it a matrix and, they call this the meet. Should have been nice if they called it matrix and, but it's the meet. All right, 2. I'm going to take the positions, Aij, and I'm going to do a bitwise OR with Bij, and this is going to be called the join. Why? Well, because they're kind of joining them. One of the ways of looking at this is a lot of times these represent the idea of elements of a set, and the overlap where these two things and, oh, it's in this one and in this one. That means it's a 1 and a 1. And so what that returns is the intersection, which is essentially where these sets meet, right? And then a union of the two says, well, let's just join everybody together. And so that's why we usually pick that term. Anyways, the third is going to be the bitwise product, which is A. Wow. You can tell what I was thinking about, what I was going to write next. It's funny. What you're saying and what you're thinking about is never the same when you're teaching. And now I need to have a different symbol besides the time symbol, and the way that we do this is we make it the O dot. And this is called the Boolean product. Again, this is a matrix, Cij. It satisfies the same things as this has to be k by m by k. This needs to be k by n. Therefore, this will be m by n on the result. But now the Cij, if we look back up above, every product that you see, we are going to make into an and every plus that you see, we are going to make into a or. And so same concept, except we do this AI1 and B1J ORed with AI2 and B2J ORed with AIK and BKJ. Now, due to the short circuit process of ands and ors, if at any time there is a 1 and a 1, you know, like, what are we doing? We're looking at the first position of the ith row and the first position of the jth. Then we look at the second elements, third elements as we start to move down. If at any time there's a corresponding 1 and 1, that would be the only time and would spit out 1. But if any of these at any time are a 1, if this was a 1 and a 1, that would be 1. But what is this operator? It's ORs. But what's 1 or anything? 1. So the moment that you have a pair 1 and 1, stop. The answer is 1. Because it short circuits it. So you actually don't have to do all the operations. If at the very beginning, it's, oh look, 1 and 1, done, 1. Well, what if it was 10 by 10? Don't worry about it. The other 9 comparisons are not necessary because it's 1 or 1 wins. It's 1. Now, on the other hand, if it's 0 or 1 and 1 or 0, okay. No, 0, 0 until the very end. You might have to do all the comparisons. But I won't obviously do a 10 by 10. You might do it in the homework, but that's just to make sure that you know how to grind out the problem. Okay, from this we could also extend to powers, but to get to powers we need to do identity and inverse. For identity, for both of these, for both normal matrices and 0, 1 matrices, the identity I is going to be ones down the diagonal and zeros everywhere else, and this is normally IN, means that this is n by n. Identity matrices need to be square. If the matrix you're multiplying is not square, the identity on the right is going to be different from the identity on the left. Matrix multiplication is not commutative. An easy way to see it is if these are non-square, that's an easy test. You just can't flip the order of multiplication, right? So you have a left side multiply and a right side multiply. So that's our identity one. If I have identity under normal matrices, if I have matrix multiply inverse, all we have for this class is check. We are not going to find inverses, right? Finding an inverse we have no interest in. We just want to verify that there are them. If you want to find an inverse and what's the determinant, when does an inverse exist, when is it singular, when is it non-singular, all those words from linear algebra, take linear algebra. All right, for us, we're just going to do this. A's inverse times A needs to be I, and A times A inverse needs to be I. You just simply show. That's the most we are going to do in this class. The book will say, hey, look, and students are like, well, I have to find, no. They said, this is the matrix, verify this is the inverse. What did they ask you to do? Multiply them. We're only interested in can you add, can you multiply, can you meet, can you join, can you Boolean product. Now, the last thing that we can have now that we have the identity is we can talk about powers, which is just simply a bunch of multiplications. What A to the 0 power is the identity matrix, and A to the R power is A times A times A times A, obviously R times. Notice that that's a normal matrix. If I have a 0, 1 matrix, the way you designate the difference is you put the power in closed brackets. And the closed brackets tell you that this is a 0, 1 matrix. That's still the identity, which is, hey, a bunch of zeros and ones. But A to the R is now A, Boolean product, A, Boolean product, A, Boolean product, A, again, R times. But now what we're doing is and, or, as we're going through the process, rather than times plus, times plus, times plus, as you're going through the operation. Again, the reason why we're going to do this is for applications. What happens is A will be used to represent a mathematical object. Normally, it would be, say, a graph, or which would be a sequence of steps, places that you can get, like a relationship. So we've talked about, functions are actually relations under the idea of set theory, right? Eventually, we represent these things with matrices. And then matrices to powers will mean particular things underneath relationships. So if a relationship is, I'm going from one location to another location, and let's say it goes back on itself, powers are follow the rules, now follow it again, now follow it again, now follow it again. If you had to follow the rules 3 times, where would you get to? And this matrix of A to the R will hold that information. So those are the types of things that we're going to use this for. Again, it's not linear algebra. This is, we are going to need to be able to add, multiply, power, meet, join, Boolean product. Those are the things we need to be able to do. The only things that are new are that. Because college algebra at the very end should have covered adding and multiplying matrices, right? And now we've just added meet, join, and Boolean product. So that's the only new stuff that we've done. All right. Last operation, transpose. And transpose is pretty easy. A transpose is just simply equal to AJI, where A is AIJ. So what are we really doing? We switch row, column. Row 1 becomes column 1. Row 2 becomes column 2. and if we switch it. All right, what's some examples that we could do just to kind of goof around?
Sorry.
All right, let's say A is equal to 1, 0, negative 1, 2, and let's say B is equal to 0, 1, 1, 3. What would be A plus B? Add them in exact positions, which would be what?
1, 1, 0.
Very good. What would be A times B? All right. Here's where recordings don't work too well. Because this really works well if you have two fingers, right? Well, that's too tough. Anyway. Like that, right? Position, pitch, position. 1 times, so I would look at row 1 and column 1 will make row 1, column 1, which is 0 plus 0 is 0. All right, so row 1, column 1 is 0, and then I would take row 1, column 2, which is going to be 1 plus 0, which is 1, and then I'll get 0 plus 2, 2, and then I get negative 1 plus 6 is 5. Everybody okay with that? You just go, like for example, row 2, column 2, negative 1 times 1 is negative 1, 2 times 3 is 6. That's why that guy is negative 1 times 1 plus 2 times 3, that's 5. Okay? Everybody know how that is those two circles up above. So we need to be able to add, we need to be able to multiply. We need to be able to multiply many times. We could do things like, hey, what would be A to the 5th power? Nobody, I'm not going to do this. 1, 0, negative 1, 2, right? Times 1, 0, negative 1, 2, 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 right? So 1, 2, 3, 4, 5. And so when you do this, you could, once you multiply those, what could you do? Those are already done, right? So I could just simply immediately collapse those two. And so then you could cut off multiple multiplications. I already did that. That's right. Right? And so you can always group in 2s and then 4s, however you want to do it, the higher you go. So I'm lazy. You do this. At home. All right, and the same idea, what if we would have A was equal to 1, 0, 0, 1, and B was equal to 0, 1, 1, 1. What would be A? Anybody remember the word for that? This symbol, sorry.
Oh.
The meat. So what would be the meat of those two? Where are 1s in both positions? That one, right? So everybody else is 0s. What would be the join? 1s everywhere. And what would be the Boolean product? I'd be 0 or 0, right? When I would do this one and this one, I would get 0 or 0, so I could just get 0 on that. So that's a 0. And then I would get, for this one, oops, did not mean to touch that. Back. If I did this one and this one, I would get 1, done, right? Oh, look, it's 1 or, who cares? It's 1, right? And then I would get 1, and then I would get 1. And there we go. There's our Boolean. So we just need to be able to do the ops. That's what I'm interested in.
Would you get 0 on the bottom?
Nope. Because second row, second column would be 0 or 1. Right? It would be this number and this number is 0, but this number and this number is 1, and 0 or 1.
I mean, on the bottom left, wouldn't that be 0, 1 and 0, 1?
No, because that one would be 0, 0, which is 0, but 1 and 1 is 1, so it's 1. That's where 2 fingers were. So, is everybody okay with that? So we just need to be able to do the ops. That's what I'm interested in. All right, attendance. You'll like this one. Man, forgot this. Right, that's example 5, page 173, right? I think. Example 5, 173. Make sure I did that right. Yep. Again, the book gives the proof in the book is not what I would want. They give you all these examples to explain how that formula is working. You don't prove by examples. When you actually do a proof, you'd leave the examples out. You would do more like what we did in class. You could use the formula that they do for the book, but they say, hey, look, here's this example. I don't want to see examples. Right? That doesn't. Examples help you think about it as you're working through it. That's not actually part of a proof. All right, that's it.